The question seems simple at first, almost too simple to carry any real weight. What is a photon made of? It sounds like the kind of thing that should have a clean answer, something you can point to, describe, and then move on from. After all, everything around us feels like it is made of something. Tables are made of wood, or metal, or plastic. Air is made of molecules. Even atoms, once thought to be indivisible, turned out to be made of smaller pieces, electrons and quarks, and deeper layers still. So it feels natural to assume that a photon, a particle of light, must also be made of something more fundamental. But the moment you begin to look closely, that expectation starts to slip. A photon is not like the objects we are used to thinking about. It does not sit still. It does not have a size in the way a grain of sand has a size. It does not have an inside and an outside. It does not even experience time in the way anything else does. The closer you try to get to it, the more it refuses to behave like a thing that could be taken apart. And that is where the question begins to change. Because instead of asking what a photon is made of, we are slowly pushed toward a more unsettling idea. What if some things are not made of anything at all? To understand why this is even a possibility, it helps to step back, not into philosophy, but into physics itself, into the way modern science actually describes reality at its most fundamental level. In everyday life, we think of the world as being built from objects. But in modern physics, especially in quantum field theory, the picture is very different. The universe is not primarily made of particles. Instead, it is made of fields. These fields are not objects in space, they are the fabric of space itself. They exist everywhere, at every point, stretching across the entire universe. There is an electron field, a quark field, and crucially, an electromagnetic field. A photon is not a tiny bead of light flying through empty space. It is an excitation of the electromagnetic field. That word, excitation, is doing a lot of work here. It means a small, localized disturbance, like a ripple moving across the surface of water. The water itself is the field. The ripple is what we observe as the particle. So in this picture, a photon is not made of smaller parts. It is the smallest possible ripple in the electromagnetic field. There is nothing inside it because it is not a container. It is a momentary pattern, a flicker of activity in something more fundamental. And this is where things start to become difficult to visualize. If you imagine a wave on the ocean, you can still point to the water molecules that make it up. The wave is a pattern, but it is a pattern of something. With a photon, there is no deeper layer beneath the field itself. The field is the most basic level we currently know. So asking what a photon is made of becomes a bit like asking what a ripple in a pond is made of. If there is no water underneath, only the ripple itself, it begins to feel like the question has nowhere to go. But the strangeness does not stop there. A photon always moves at the speed of light. Not sometimes, not under certain conditions, but always. There is no way to slow it down, no way to bring it to rest. And because of this, something very unusual happens when we try to describe its experience. From the perspective of relativity, as an object moves closer and closer to the speed of light, time begins to slow down for it. At the exact speed of light, this effect becomes extreme. Time, in a very real sense, stops. For a photon, there is no passage of time between the moment it is emitted and the moment it is absorbed. It could be created in the heart of the star, travel across millions of years of space, and then be absorbed by your eye. Yet from its own perspective, if such a perspective can even be meaningfully defined, that entire journey has no duration at all. It simply exists at emission and then at absorption with no in-between. So now the idea of it having an internal structure becomes even more difficult to hold on to. Structure implies persistence over time, an arrangement of parts that continues from one moment to the next. But a photon does not experience moments in that way. It is less like an object moving through time, and more like a connection between two events. And even calling it a connection may not be quite right. Because when we try to measure a photon, to pin down where it is or what it is doing, we run into another layer of complexity. The photon does not behave purely like a particle, nor purely like a wave. It exists in a strange middle ground that does not fully resemble either. In some experiments, it arrives as a single, discrete point, as though it were a tiny particle hitting a detector. In others, it spreads out, interferes with itself, and behaves like a wave passing through multiple paths at once. This is not because it switches between being a wave and being a particle. It is because those are the closest analogies we have, drawn from a world that operates very differently. A photon is something more abstract. And when you start to accept that, the original question begins to dissolve even further. Because if a photon is not an object, not something with an inside, not something that persists through time in a familiar way, then asking what it is made of may be the wrong kind of question entirely. It is like asking what a note in a piece of music is made of. You can describe the vibration of air, the movement of strings, the pressure waves reaching your ear. But the note itself is not a separate substance. It is a pattern, a temporary arrangement of energy and motion. A photon is closer to that kind of existence. It is not a thing sitting inside the universe. It is something the universe does. And that shift, from things to processes, from objects to patterns, is one of the quiet but profound changes that modern physics asks us to make. Because once you start seeing the world this way, the idea that everything must be built from smaller and smaller pieces begins to feel less certain. Instead, you begin to see a different kind of structure, one where the most fundamental layer may not be made of parts at all. The photon sits right at the edge of that realization. It is one of the simplest things we know, and yet the more closely you examine it, the more it seems to resist every attempt to break it down further. And that raises a deeper question, one that is harder to answer and perhaps more interesting to sit with. If a photon is not made of anything, then what does it really mean for something to exist at all? Because at that point, the answer is no longer about particles or fields or equations. It becomes something much quieter, something that does not resolve cleanly, something that lingers just beneath the surface of the question itself. If we stay with that idea for a moment, that a photon is not a thing but a pattern, then the next step is to understand what kind of pattern it actually is, because this is where the description becomes more precise, and also more difficult to reconcile with intuition. In quantum field theory, the electromagnetic field is not just a background that supports photons, it is the fundamental entity, and what we call a photon is the smallest possible unit of excitation that this field can sustain. This is not a metaphor in the loose sense. It is a mathematically defined statement about how energy can exist within that field. The field can be excited in many ways, but only certain discrete amounts of energy are allowed, and each of those minimal packets is what we observe as a photon. This discreteness is important because it tells us that a photon is not divisible in the way larger structures are. You cannot take half of a photon and still have something that behaves like light in the same way. If you reduce its energy, you do not split it into smaller photons, you simply change its frequency, shifting it along the electromagnetic spectrum. A high-energy photon might appear as gamma radiation, while a lower energy one might be visible light, or even radio waves, but in each case, it is still a single excitation, still a single photon. There is no internal component that can be peeled away. no substructure waiting beneath the surface. This is where the comparison with other particles becomes useful, because not everything in physics is this simple. Protons and neutrons, for example, are made of quarks, bound together by the strong force, and those quarks themselves are described by their own underlying fields. In those cases, asking what something is made of leads to a meaningful answer, because there is a deeper layer to uncover. But when it comes to photons, every experiment we have ever conducted suggests that there is no such layer beneath them. They appear to be fundamental, not because we have failed to look closely enough, but because all of our best theories, tested to extraordinary precision, describe them as having no internal structure at all. And yet, even here, there is a subtle tension, because calling something fundamental does not necessarily mean it is the final word. It simply means that within our current understanding, there is nothing smaller that composes it. Physics has a long history of revising what it considers fundamental, and it is always possible that a deeper theory could one day reveal a new layer beneath what we now take as basic. However, any such theory would have to reproduce everything we already know about photons, including their lack of size, their constant speed, and their precise interactions with matter. So, if there is something deeper, it is hidden in a way that leaves no trace in the behavior we can currently measure. There is also the question of how a photon carries energy and momentum without having mass, because this is another place where everyday expectations begin to fail. In classical thinking, momentum is tied to mass and motion. Something heavy moving quickly carries more momentum than something light moving slowly. But a photon has no rest mass at all, and yet it clearly carries both energy and momentum, enough to exert pressure, to push on surfaces, to transfer energy across vast distances. This is not a small effect either. It is measurable, and in some contexts, like solar sails or radiation pressure in stars, it becomes a dominant force. The key to understanding this lies in the relationship between energy, frequency, and wavelength. A photon's energy is directly tied to its frequency. The higher the frequency, the more energy it carries. Its momentum, in turn, is related to its wavelength. So even without mass, it still participates fully in the dynamics of motion and interaction. This again reinforces the idea that a photon is not a tiny object with hidden parts, but a specific configuration of the electromagnetic field, defined by its energy and its oscillation. And still, something about this remains unresolved at a deeper level, because even if we accept that a photon is an excitation of a field, we can still ask what the field itself is made of, or why it exists at all. This is where the explanation reaches a boundary, not because physics stops working, but because it stops reducing things any further. The electromagnetic field is treated as fundamental, something that simply exists as part of the structure of reality, and photons are the smallest disturbances that can move through it. At this point, the question begins to invert. Instead of asking what a photon is made of, we are left asking why reality is structured in such a way that something like a photon can exist in the first place. Why should there be a field that allows for these discrete excitations, and why should those excitations behave in such a consistent and universal way across the entire universe? There is no simple answer to that, and it is not the kind of question that can be resolved by looking deeper inside the photon itself, because by every measure we have, there is no inside to examine. The photon does not conceal anything beneath its surface, because it does not have a surface in the conventional sense. It is already at the level where the description stops being about composition and starts being about behavior. And perhaps that is the quiet shift that sits underneath all of this. The idea that the most fundamental aspects of reality may not be built from smaller pieces, but instead defined by the rules they follow, by the way they interact, by the patterns they form and the constraints they obey. In that view, asking what something is made of becomes less important than understanding how it behaves, because behavior is all there is at that level. The photon, simple as it seems, sits right at the center of that shift. It carries energy. It defines how we see the universe. It links distant events across space. And yet when we try to take it apart, there is nothing there to separate. It is already as simple as it can be, and that simplicity is not a lack of detail, but a sign that we have reached something close to the foundation of our current understanding. And even then, there is a sense that something remains just out of reach, not hidden inside the photon, but in the deeper question of why the universe is built in this way at all. If we follow that line of thinking a little further, another layer begins to emerge, one that is less about what a photon is in isolation and more about how it exists in relation to everything else. Because one of the most subtle but important aspects of a photon is that it never really exists alone in the way we imagine objects to exist. It is always part of an interaction, always part of a transition between states, always tied to the behavior of something else, whether that is an atom, a charged particle, or the structure of the electromagnetic field itself. When an electron in an atom drops from a higher energy level to a lower one, a photon is emitted. When that photon is later absorbed, another electron transitions upward. At no point is the photon simply sitting there as a stable, independent object waiting to be examined. It is created in one event and absorbed in another, and its entire identity is defined by that exchange. This makes it difficult to treat it as a standalone entity, because its existence is inseparable from the processes that generate and detect it. This becomes even clearer when you look at how photons are described mathematically. In quantum electrodynamics, which is one of the most precise and successful theories ever developed, photons appear as the carriers of the electromagnetic force. They are not just passive messengers of light, they are the mechanism through which charged particles interact with each other. When two electrons repel one another, this interaction can be described as an exchange of photons, not necessarily real photons that could be detected directly, but virtual ones, fleeting disturbances that mediate the force. These virtual photons complicate the picture even further, because they do not behave in the same way as the photons we can observe. They do not need to obey the same constraints on energy and momentum, and they cannot be isolated or measured directly. Yet they are essential to the structure of the theory, and without them, the interactions we observe would not be described correctly. So now, the photon is not just a ripple in a field, but also part of an underlying network of interactions that never fully resolves into simple, tangible objects. At this point, it starts to become clear that the idea of what it is made of belongs to a different level of description, one that works well for larger, composite systems, but begins to fail as we approach the fundamental layer. In that deeper layer, the language shifts away from composition and toward interaction, probability, and symmetry. A photon is defined not by its internal ingredients, but by the role it plays within the structure of the theory. And symmetry, in particular, is a key part of that structure. The existence of the photon is deeply tied to a symmetry in the laws of physics known as gauge symmetry. Without going into the full mathematical framework, this symmetry essentially ensures that certain transformations in the electromagnetic field do not change the observable physics. The requirement that this symmetry holds leads directly to the existence of the photon as a massless particle that mediates the electromagnetic interaction. So, in a very real sense, the photon exists because the universe is built in a way that preserves this symmetry. It is not an add-on or a separate component, it is a necessary consequence of the underlying rules. If the symmetry were different, the photon as we know it would not exist, or it would behave in a completely different way. This is a very different way of thinking about existence. Instead of asking what something is made of, we begin to ask what principles require it to exist. The photon is not assembled from smaller parts, it is implied by the structure of the laws themselves. It is something that must be there if those laws are to remain consistent. And this brings us back to the question of why photons have no mass, because this is not just an arbitrary feature, it is deeply connected to that same symmetry. If the photon had even a tiny amount of mass, the electromagnetic force would behave differently. It would not extend infinitely, and the familiar inverse square law would break down over large distances. The fact that light travels exactly at the speed it does, and that electromagnetic interactions behave the way they do, is tied to the photon being massless. Experiments have tested this with extraordinary precision, looking for even the smallest deviation that might suggest a non-zero mass, and so far, nothing has been found. Within the limits of our measurements, the photon appears to be perfectly massless, and this again reinforces the idea that it is not hiding any internal structure that might give rise to mass in the way composite particles do. There is also something quietly remarkable about the way photons interact with each other, or more precisely, the way they usually do not. In classical electromagnetism, light waves pass through each other without any interaction at all, as though they are completely unaware of one another. In quantum theory, there are extremely rare conditions under which photons can scatter off each other, but these effects are so weak that they are almost never observed in everyday circumstances. This means that photons can travel across vast distances through dense regions of radiation without losing their identity or being disrupted in any meaningful way. A photon emitted billions of years ago can reach us today, carrying information about its source, almost unchanged. It does not decay, it does not wear down, it does not fragment into smaller pieces. It simply continues until it interacts. That persistence, combined with the absence of internal structure, makes the photon feel less like a conventional particle and more like a stable unit of behavior, something defined entirely by its properties and its interactions, rather than by any hidden composition. It is as though it exists only in terms of what it does, not what it is made of. And yet, even with all of this, there is still a limit to how far the explanation can go, because the fields themselves, the symmetries, the mathematical structures, all of these are descriptions that work with extraordinary accuracy, but they do not necessarily tell us why those structures exist in the first place. They describe the rules, but they do not explain why those rules are the ones that govern reality. So when we ask what a photon is made of, we are really pressing against the edge of that boundary. We are trying to apply a question that assumes there is always a deeper layer, always something smaller, always something more fundamental waiting to be discovered. But the photon, as far as we can tell, sits at a level where that assumption no longer holds in the same way. It is not that the question is meaningless, but it begins to transform into something else, something less about physical composition and more about the nature of the laws themselves. And in that shift, the photon becomes less of an object to be dissected and more of a clue, a signpost pointing toward a deeper structure that may not be built from parts at all, but from relationships, constraints, and patterns that do not reduce any further. And that is where the sense of incompleteness begins to settle in. Not because the photon is missing something inside it, but because our way of asking the question may not be suited to the kind of answer that reality is able to give. If we continue along this path, there is another detail that quietly reshapes the entire picture, and it comes from something that at first seems almost trivial. A photon has no rest frame. This is not just a technical statement. It has deep consequences for how we think about what a photon even is. For any object with mass, you can always imagine the point of view where that object is at rest. From that perspective, you can describe its internal structure, its size, its evolution over time. But for a photon, no such perspective exists. There is no frame of reference in which a photon is stationary, and because of that, many of the usual ways we describe physical things simply do not apply. This absence of a rest frame means that concepts like length and duration begin to lose their usual meaning when applied to a photon. In special relativity, as something approaches the speed of light, lengths in the direction of motion contract, and time intervals stretch. But the exact speed of light, these effects reach their extreme limits. So if you try to imagine looking inside a photon, there is no consistent way to define what that would even mean, because there is no frame in which the photon can be said to have an internal spatial extent that persists over time. The idea of internal structure depends on being able to freeze something in place and examine it, but a photon can never be frozen in that way. This connects back to why every experimental attempt to probe the photon at smaller and smaller scales has found no evidence of substructure. High-energy collisions, scattering experiments, and precision measurements all point to the same conclusion. Within the limits we can test, the photon behaves as a point-like particle, with no measurable size and no internal components. If there were smaller parts inside it, those experiments would begin to reveal deviations from the predictions of quantum electrodynamics, but they do not. The theory continues to match observations with astonishing accuracy. There is also an interesting contrast here with particles that do have mass. Even when those particles are treated as fundamental in the same theoretical framework, like electrons, they still allow for a rest frame, and that gives us a more familiar way to think about them. We can imagine an electron sitting still. We can talk about its properties in a way that feels anchored to a stable point of view. With photons, that anchor disappears, and we are left with something that only ever exists in motion, only ever exists as part of a process unfolding at the speed of light. And this leads into another subtle but important idea, which is that the properties of a photon are inseparable from its motion. Its energy, its frequency, its wavelength, all of these are defined in relation to how it is moving through space and time. There is no underlying object that carries these properties in a static sense. Instead, the properties themselves are the description of the photon. Change the frequency, and you have effectively changed the photon, not just adjusted something about it. This becomes particularly striking when you consider phenomena like redshift. As a photon travels through an expanding universe, its wavelength stretches and its energy decreases. Over vast distances, a photon emitted as visible light can be shifted into the infrared or even into radio wavelengths. Nothing has been removed from it, nothing has been broken apart, and yet its properties have changed continuously as it moves. This reinforces the idea that a photon is not a fixed object with a stable internal composition, but a dynamic excitation whose identity is tied to its current state within the field. There is also the question of localization, which turns out to be far more complicated than it first appears. In everyday thinking, we imagine particles as being located at specific points in space. But in quantum mechanics, a photon is described by a probability distribution, a spread-out wave function that tells us where it might be found if we measure it. This distribution can extend over large regions, and only when a measurement is made does the photon appear to collapse to a specific location. This does not mean the photon is physically spread out in the same way a cloud is spread out, but it does mean that its position is not a fixed, well-defined attribute prior to measurement. So again, the idea of a compact object with an internal structure becomes harder to sustain. If you cannot even say exactly where the photon is before you interact with it, and the notion of examining its internal composition becomes even more abstract. And yet, despite all of this, photons are incredibly well behaved, in the sense that their interactions are governed by precise, predictable rules. When a photon is absorbed by an atom, the energy transfer matches exactly the difference between quantized energy levels. When photons are emitted in processes like atomic transitions or particle interactions, their properties follow strict conservation laws. This consistency is not a sign of hidden complexity inside the photon, but rather a reflection of the underlying structure of the field and the symmetries that govern it. At this stage, the pattern that keeps reappearing is that every time we try to treat the photon as a small object with parts, the description breaks down, but when we treat it as a fundamental excitation defined by its relationships and constraints, everything falls into place with remarkable precision. The theory becomes simpler, the predictions become clearer, and the need for an internal structure disappears. There is, however, one more angle that adds depth to this picture, and it comes from the way photons relate to information. A photon can carry information across space, encoded in its frequency, its polarization, its phase. This is the basis of everything from vision to communication technologies to the study of distant galaxies. But this information is not stored in a physical container inside the photon. It is expressed through the state of the excitation itself, through the way the electromagnetic field is oscillating. So once again, the photon resists being thought of as a thing with an interior. It is better understood as a state, a configuration, a specific way in which the field is behaving at a given moment. And that behavior can be incredibly rich, capable of encoding complex patterns, yet it does not imply any deeper layer of components that make it up. At this point, it becomes increasingly difficult to maintain the original intuition that everything must be composed of smaller pieces. The photon stands as a clear example of something that appears to be fundamental, not just in the sense that we have not yet found its parts, but in the sense that the very framework we use to describe it does not require any such parts to exist. And this is where the question begins to turn inward again, not toward the photon itself, but toward the assumptions we bring with us when we ask about it. The expectation of composition, of layers within layers, is something that comes from our experience with larger, everyday objects. But at the deepest level we can currently probe, reality may not be structured that way at all. Instead, it may be built from entities that are defined entirely by their properties and their interactions, with no underlying substance in the traditional sense. The photon is one of the clearest and simplest examples of this idea, and at the same time one of the hardest to fully accept, because it asks us to let go of a way of thinking that feels almost unavoidable. And even as we get closer to that acceptance, there is still a lingering sense that something is missing, not inside the photon, but in our understanding of why the universe allows such entities to exist in the first place. If we take one more step deeper into this, the next shift is subtle, but it changes the feeling of the entire question. Up to this point, we have been treating the photon as something that exists within space, moving through it, carrying energy from one place to another. But there is another way to frame it, one that is closer to how the mathematics actually treats these processes. And in that framing, the photon is not just moving through space, it is inseparable from the structure of space-time itself. The electromagnetic field does not sit inside space as a separate substance. It is part of what space is. So when a photon propagates, what we are really describing is a disturbance that is woven into the geometry and behavior of space-time. It is not traveling across a background in the way a ball travels across a surface. It is a change within that background, something that cannot be cleanly separated from it. This becomes more apparent when you consider how light defines the structure of space-time in relativity. The speed of light is not just a property of photons, it is a fundamental limit that shapes the causal structure of the universe. It determines what events can influence one another, how signals propagate, and how time and space are related. In that sense, the photon is not just another particle among many. It is tied directly to the deepest constraints of the universe. So now the question shifts again, because if the photon is bound up with the structure of space-time itself, then asking what it is made of starts to feel even more misplaced. It is not sitting on top of something more fundamental. It is part of the framework that defines what more fundamental even means. There is also a quiet implication here about how far reductionism can really go. For a long time, physics has made progress by breaking things down into smaller and smaller components. Atoms into nuclei and electrons, nuclei into quarks, and so on. But the photon represents a point where that strategy stops yielding new layers, not because we have given up, but because the theory itself does not point toward further subdivision. Instead, what becomes more important is understanding the relationships between these fundamental entities. How fields interact, how symmetries constrain behavior, how conservation laws emerge from deeper principles. The focus shifts from what things are made of to how they fit together into a coherent whole. And there is something else that begins to emerge from this, something that is less often stated directly. The photon is not just fundamental in isolation, it is fundamental in a very specific way. It is the quantum of a force, the smallest unit through which electromagnetic interactions occur. This means that its existence is tied not just to the presence of the electromagnetic field, but to the very idea that forces can be mediated by discrete exchanges. In other words, the photon is not just a building block, it is part of the mechanism that allows building blocks to influence one another. It sits at the interface between things, rather than inside them. And that position, between objects rather than within them, is another reason why the question of its internal composition becomes difficult to sustain. If you imagine trying to take apart a force, the idea quickly becomes unclear. A force is not something that contains pieces in the usual sense. It is something that happens, something that acts between objects. The photon, as the quantum carrier of that force, inherits some of that character. It is not just an entity, it is an interaction in motion. This is also why photons play such a central role in how we observe the universe. Every time we see something, we are detecting photons that have interacted with matter and then reached our eyes. Every telescope, every camera, every optical instrument is built on this same principle. Photons are the messengers that connect distant events to our local experience. But even calling them messengers can be slightly misleading, because it suggests that they carry information in a passive way, like a letter being delivered. In reality, the act of carrying information is itself an interaction, and the properties of the photon are shaped by the conditions under which it was emitted and the environment through which it has traveled. It is not just transporting information, it is embodying it in its state. This leads into an even more subtle point, which is that the photon does not have a fixed identity independent of measurement. In quantum theory, what we can say about a photon is always tied to how we choose to measure it. If we measure its position, we get one kind of description. If we measure its momentum, we get another. These descriptions are not simply revealing pre-existing properties, they are part of how those properties are defined. So once again, the idea of a small object with hidden internal components begins to feel less appropriate. There is no stable, underlying thing whose pieces we can catalogue. Instead, there is a set of potential behaviors, constrained by the laws of physics, that become actualized in specific interactions. At this stage, the photon begins to feel almost like a boundary case, something that sits right at the edge of what we can meaningfully describe using everyday concepts. It is not quite an object, not quite a process, not quite a wave, not quite a particle, but something that shares aspects of all of these without fully reducing to any of them. And that is perhaps why the question of what it is made of persists, even when the theory suggests that there is nothing further to find. The question itself comes from a deeper instinct, the sense that reality should always have another layer beneath it, something more solid, something that explains everything else. But the photon quietly resists that instinct. It does not reveal a deeper layer when we look inside it, because there is no inside in the way we expect. It is already at the level where explanation shifts from composition to principle. from substance to structure. There is still, however, one more direction to explore, and it brings us to the limits of our current theories. Because while quantum field theory describes photons with extraordinary success, it does not include gravity in the same framework. The electromagnetic field fits neatly into the quantum picture, but space-time itself, as described by general relativity, is not yet fully reconciled with that quantum description. This raises the possibility that at an even deeper level, the concepts we are using now, fields, particles, space-time, may themselves be approximations of something more fundamental. In some approaches to quantum gravity, space-time is not continuous, but emerges from a more basic structure. In others, fields themselves are not fundamental, but arise from deeper, more abstract entities. If that is the case, then the photon might not be truly fundamental in an absolute sense, but only within the framework we currently understand. There could be a deeper layer where even the idea of a field excitation breaks down into something else entirely. But what is striking is that even in those speculative theories, the photon does not appear as something with internal parts in the traditional sense. Instead, it would emerge as a feature of a deeper structure, much like it already emerges from the electromagnetic field in our current understanding. The pattern repeats, not as a set of smaller pieces, but as a shift in the level of description. So even when we push beyond the standard model, the idea that a photon is made of something in the usual sense becomes harder to maintain. The deeper we go, the more the language of composition seems to give way to the language of emergence and structure. And that leaves us in a quiet but interesting position, where the original question has not been answered in the way we might have expected, but it has been transformed into something broader, something that touches on the very way we think about reality itself. If we let that idea settle for a moment, that what we call a photon may not be a final building block but rather an expression of something deeper, then the next question begins to feel less like a technical one and more like a shift in perspective. Because throughout all of this, there has been an assumption quietly guiding the question. The assumption that reality is built in layers, that if you keep peeling things back, you will eventually reach something solid, something that everything else is made from. But the photon challenges that assumption in a very particular way. It does not just resist being broken down further. It suggests that the very act of breaking things down may not always be the right approach. At some level, explanation may stop being about smaller pieces and start being about patterns that do not reduce any further. This is not entirely unfamiliar, even outside of physics. There are systems where the behavior matters more than the components, where the pattern is the thing that exists, not the material it is made from. A melody is not defined by the instrument that plays it. A whirlpool is not defined by the individual water molecules passing through it. In both cases, what persists is the structure, not the substance. The photon begins to feel more like that kind of entity. It is not something that contains smaller things. It is something that is defined by the way a field behaves, by the constraints it follows, by the relationships it participates in. And those relationships are not secondary, they are the entire description. There is also a sense in which the photon forces us to confront the limits of visualization. Much of our intuition comes from imagining things in space, picturing shapes, boundaries, and internal parts. But the deeper you go into modern physics, the less useful those images become. The mathematics continues to work with extraordinary precision, but the mental pictures begin to fall apart. When we say a photon is point-like, we are not imagining a tiny sphere with no size. We are saying that every experiment we can perform treats it as having no spatial extent. When we say it is an excitation of a field, we are not picturing a ripple in a familiar medium. We are describing a change in something that does not have a direct analog in everyday experience. The language remains, but the meaning becomes more abstract. And this is where the discomfort often comes from, because it feels like something is missing, as though we have described how a photon behaves without ever quite saying what it is. But that discomfort may be telling us something important. It may be pointing to the fact that at a certain level, what it is and how it behaves are no longer separate questions. For a photon, there is no hidden layer beneath the behavior that needs to be uncovered. The behavior is the thing itself. This is also reflected in how precisely the theory predicts its interactions. Quantum electrodynamics is one of the most accurate theories ever tested, with predictions that match experimental results to an extraordinary number of decimal places. If the photon had internal structure, if it were composed of smaller parts, those interactions would almost certainly show small deviations, tiny inconsistencies that would accumulate in precise measurements. But they do not. The equations continue to hold, the predictions continue to match, and the photon continues to behave as though it is exactly what the theory says it is. Nothing more, nothing less. There is something almost quiet about that consistency. Not dramatic, not surprising in a sudden way, but persistent. The more closely we look, the less there seems to be to uncover inside the photon itself. Instead, all of the richness appears in how it interacts, how it connects, how it fits into the wider structure of the universe. And that wider structure is where the deeper mystery begins to shift. Because if the photon is not made of anything in the traditional sense, then the question of composition does not disappear. It moves outward. It becomes a question about the fields, about space-time, about the underlying principles that give rise to everything we observe. Why do these fields exist? Why do they have the properties they do? Why are the symmetries arranged in such a way that photons emerge at all? These are not questions that can be answered by looking inside a photon, because the photon is already a surface expression of those deeper rules. It is like trying to understand the laws of fluid dynamics by examining a single ripple. The ripple reflects those laws. It embodies them, but it does not contain their origin. At this point, the sense of direction begins to change. Instead of moving inward, searching for smaller and smaller components, the investigation begins to move outward toward the structure of the theory itself, toward the constraints that shape everything we observe. And in that outward movement, the photon becomes less of a target and more of a guide. It shows us where our usual intuitions stop working, where the idea of what is it made of gives way to a different kind of question, one that is less about substance and more about why the universe is organized in this particular way. There is also something else that becomes noticeable here, something that sits just beneath the surface of all of these descriptions. The fact that the photon, despite being so abstract, is one of the most familiar things in our experience. Every time you open your eyes, every time you see color, brightness, contrast, you are interacting with photons. They are the medium through which the entire visible world is presented to you. And yet, the thing that carries all of that information, that makes the world visible at all, turns out to have no internal structure, no hidden components, no deeper pieces that it is built from. It is as though the most immediate aspect of reality is carried by something that resists being understood in the most intuitive way. That contrast is difficult to ignore. The closer something feels to us, the more we expect it to be simple and tangible. But with photons, the opposite seems to be true. The more familiar they are in experience, the more abstract they become when we try to describe them precisely. And so the question remains, but in a different form now. No longer asking what a photon is made of, but asking what kind of universe allows something like a photon to exist at all, something that behaves with such precision, carries energy and information so reliably, and yet contains no internal structure that we can uncover. That question does not close easily. It does not resolve into a neat answer. It lingers, not as a gap in the theory, but as a boundary of understanding, a place where the explanations we have remain complete in one sense, and yet still leave something deeper untouched. And it is right at that boundary that the photon continues to sit, simple, fundamental, and quietly unresolved. And if we stay with that boundary for just a moment longer, something begins to settle into place, not as a final answer, but as a different way of holding the question itself. Because throughout all of this, the photon has not revealed a hidden interior. It has not broken apart into smaller constituents. It has not led us downward into another layer of structure in the way so many other discoveries in physics have done before. Instead, it has done something quieter. It has redirected the question. It has shown that there are points in our understanding where asking what something is made of no longer moves us forward, where the idea of composition reaches a natural limit, and where explanation begins to take on a different shape. At that level, what matters is no longer what sits inside something, but the rules that define how it exists at all. The photon exists as a solution to those rules, as a necessary feature of a universe governed by the symmetries and constraints we have come to describe through physics. It is not assembled, it is not constructed, it is not built from smaller parts waiting to be uncovered. It is already at the level where the description becomes complete in terms of behavior, interaction, and consistency. And yet, that completeness does not feel like closure. Because even if we accept that a photon is an excitation of the electromagnetic field, even if we accept that the field itself is fundamental within our current theories, there is still a quiet sense that the explanation has stopped one step short of something deeper. Not because anything is missing from the theory, but because the theory itself rests on structures that are simply taken as given. Why these fields? Why these symmetries? Why these laws? The photon does not answer those questions, but it points directly toward them. It sits at the edge of what we can describe and, in doing so, highlights the shape of what we cannot yet explain. It becomes less like an object of study and more like a boundary marker, something that tells us where our current understanding transitions into something more open. There is also something quietly elegant about the fact that the photon, one of the simplest entities in our theories, is also one of the most essential. It carries energy across the universe, it allows stars to shine, it makes vision possible. It links distant events across vast stretches of space and time. It is everywhere, constantly in motion, constantly mediating interactions, and yet it remains fundamentally indivisible in the way we have come to understand it. It does not age, it does not decay, it does not evolve internally. It exists in the moment it is created, and in the moment it is absorbed, and in between, there is no internal story unfolding, no hidden process taking place inside it. There is only the propagation of the excitation itself, defined entirely by the structure of the field and the geometry of space-time. And perhaps that is where the question finally comes to rest, not as something answered, but as something transformed. Because asking what a photon is made of assumes that everything must ultimately reduce to smaller and smaller pieces, that there must always be something beneath the surface. But the photon suggests that this way of thinking has limits, that there may be a level at which reality is no longer composed in that way. Instead, it may be defined by patterns that do not reduce, by principles that do not decompose, by structures that are complete in themselves. The photon is one of the clearest expressions of that idea, not because it explains everything, but because it quietly refuses to be explained in the way we expect. And in that refusal, it leaves us with something that feels less like a gap and more like an invitation. An invitation to rethink what it means for something to exist, to move away from the instinct to look inside everything, and instead to consider that at the deepest level, there may be nothing inside at all. Only behavior. Only relationships. Only the structure of the universe expressing itself in the simplest possible form. And in that sense, the photon is not hiding anything from us. It is already, in a very real way, exactly what it appears to be.